I hope you had a good Labor Day break. We had some pleasant weather, and then we had some cool weather. But at least it wasn't too hot. I'm going to go over some things I want to review with you, point out some additions to our website, and then get into the items I've listed for today's session, just the key ideas for today's session. And more people may be coming in as we go along. Okay, so remember, you can just spit out your questions or type them into the chat window, and I'll add them here to our paper. And this is being recorded, so that's working well. If you guys are consuming some of the recordings, maybe you watch again, maybe you don't. I'm not asking you to watch anything again, but maybe you're checking them out if you missed a session. So this will all be scanned. Everything we write here will be scanned. And we have our whiteboard here in case we need the whiteboard. What I've found, and you can tell me whether you like this or not, I'm bringing in another person here. What I've found is that, I want to write solutions for you so you can see how I write, because that's really important to learn how to write. But I also want to make short videos of solutions, because I don't know which is a faster turnaround time. I really don't know. So I've posted a couple more videos, and you can say whether you like written solutions or video solutions, but I think I'll probably go along doing both. Let's pop over to our website for just a second, just so I can cover things that we've got posted there. So remember, this is our main page. And right now it's been adjusted to week 2. And on the week 2 introductory page, I'll just give you a rough idea of what we're working on this week, this very abbreviated week. I added 2 notes down here. Let me blow up this thing here. I have a friend who runs the honors program at Delta College, Mark Brown. So he wanted to share information with students about the honors program, which is a very open and diverse program. So people might think, oh, I need to have special qualifications, or, oh, I need to be this high or this good. No, just watch that video. He explains it to you really nicely. So you might, and there are some benefits to being in the honors program. The tutoring center at Delta College is operating this semester, and they have different methods for you to ask questions or connect with a tutor, many of them online, but some of them in-person appointments. So I don't know what your availability or interest is, but you can visit the tutoring center or chat with the staff, ask them what they have available, and on their webpage they demonstrate what they have available. So are online class sessions useful? Probably not as bad as people thought they would be. And maybe online tutoring sessions could be also similarly pretty effective, maybe more effective than you would have expected. Okay, I'm going to dump into week 2 right here. And remember, every week you're scanning our weekly webpage, because every week you see the outline, homework, handouts, video, any technology or demonstrations I'm posting, and upcoming information about the exams. We're still getting settled into the course, so I will start to become more specific about the exams shortly, maybe in a week or so. But on our outline here, you see that we had no class on Monday, September 7th. Officially, it was the college's Labor Day break, Monday and Tuesday. So I actually didn't hold office hours there. I didn't explicitly say that there was no office hours on Monday or Tuesday, so I know some people just popped in just to say hello, and I may not have caught you. So if so, I apologize. But if the college is on an official closure, I will still answer email and communicate with you, but we wouldn't have any meetings. So we have a very nice program today in section 1.4 and 1.5, just helping you get the idea of trigonometric function glued into your mind. So I think that'll help you out a great deal, especially on your computer and written homework. But speaking of homework, remember, either slide down the page or click the button. Okay, very good question. Thank you, Austin. Let me get to that. Here's the homework, and you see the dates they are due and the sections that you're to cover in the XYZ homework. So we're just getting everybody into the system. You guys are working in the system. I've scanned it a couple times just to see roughly where people are, nothing too specific. But you have until next Tuesday, 11:59 p.m., remember that's our standard deadline, to complete these 5 sections in the homework. Still adding people into this meeting. Okay, so I'm doing a better job trying to keep an eye on the waiting room. I have posted your first written homework. Now, remember the goal of the written homeworks is not high volume, but it's to help you practice writing things completely and accurately, to practice explaining something to someone. Just having the number doesn't convince anyone that you have the right number or that you knew how you got the number. So you want to know how you explain problems to them. I'm just doubling check. Don't you have homework? First of all, give me a ping because I had this problem with my recording before. I understand that we're all looking at my website right now. Is that correct? Or are you seeing maybe just that goofy icon again? Type that into the chat window if you're seeing our website. Got it. Okay, perfect. Just want to make sure I wasn't screwing that up. Right. So at the beginning, I was not going to be aggressive about the homework deadlines here. I said, okay, I'll make homework due in the second week. And then I said, no, that's a half week holiday, people getting into the system. So where is the homework? Right here. What are the due dates? Right here. So make sure you're scanning every week our weekly page so you see the homework and the due dates. Also on the resources page, I won't jump to that right now, is a list of all of these homeworks and all of the due dates. So if you click on homework 1, this is the first homework problem I want you to do. It's not very different than a problem in the book, but I just want you to show me how you would write it. I want to see your process, neatly as possible, everything like that. Now, you may have a printer, you may not. You may have access to a printer, you may not. If you have access to a printer, you could just print this out, write on it, and create an image that you could turn into a PDF and submit. If you don't, you could write this problem down. I'll try not to be so wordy in every problem, but you could write the problem down and then do the work and then take an image that you create a PDF on. So one way or the other, whether you write this yourself on a piece of paper or whether you just print this and write on it, I don't mind. I don't mind if you have more than one sheet of paper, but depending on what the problem looks like this week. But I want you to write clearly and darkly so I can read it. And then when you make your image, turn it into a PDF file, portable document format. And I can help you do that a little bit, but that should be pretty standard on any phone or computer. And I remember I gave you 2 apps that you could possibly have on a phone, but you may be able to also do this on a computer or a scanner, kind of old school. So that is a single problem. You can you can write more if you want, just bring it in one file. So I go back to my website, and this, remember, is the Dropbox. Just when you're ready to upload that file, you just click on that link and you can submit the file right there, time stamped. It'll put the time on it that you handed in. Okay, I go backwards, and the deadline is September 15 at 11:59 p.m. And I'll also give you a heads up about the next one and the next one. So I'll post more of these as we go along. After we're done, I will post the answer. After the deadline is passed, I will post an answer just in case you want to see how I did it. You might do it better, longer, shorter, not complete. I am not saying that I'm creating like the best or the only answer. I'm just saying I will post a good answer that you can look at and rely on. Okay, good. Then we got handouts, we got class notes and office hour notes. If anybody is in the office hour, we have a lot of handouts here, and I'll flash by one or two of them. I don't know if you looked at the rationalizing denominators handout. Let me double check the audio. I think I'm in audio. My audio is on. You might have to turn your microphone up if you're having trouble with the hearing. Or I'm sorry, your speaker up. Okay, let me go back to my webpage. So that's good. Pop in questions like that if you're having any questions. Did you look at the rationalizing denominators handout, which is right here? I think I might make these direct links later, but the idea that when you create trigonometric values, sometimes you have square roots, and sometimes they're in the numerator, sometimes they're in the denominator. It's just a rough idea in mathematics that people preferred square roots not to be in the denominator. And so if you need to change something like 5 divided by 5 root 2, 1 over root 2, if you need to change that into a fraction that doesn't have a radical in the denominator, that process is called completing, or is called rationalizing the denominator. So I explained it there, and then I gave several examples. Where did I give them? Right here, if you want to see rationalizing the denominator. Now, most often we're going to do this with numbers, so, and square roots, almost never with cube roots, almost never with variables in the radical, but sometimes. So most common way we're going to do this is with this first example, or maybe the sixth example here. But it's always good to practice rationalizing denominators. And here's the rule for your homework. If it says you must rationalize denominators, then you must rationalize the denominators. If it does not say, you are free to leave a radical in the denominator. Maybe later I'll talk about why people care about that, but it's not earth-shattering, so we're not going to do it today. I've got some video here. I'm starting to get things organized in videos, so I don't know if you've checked into this. The class session videos are going to drop you to a YouTube playlist, and we've only had 2 class sessions so far. But as we go along, we'll get to collect stuff in here. I just have a YouTube channel where I run several classes. So you're free to look at any of the classes I have here, but your class is right here. Plain trigonometry. So here's some class session videos, some recommended problem videos. Again, I think I just have a couple up there. And some other videos about topics. And this was the 3 famous triangles topic. So you can request any recommended problem or topic, other problem. This is where the videos will land, but they will be linked to here on our website. So recommended problem 1, chapter 1, section 5, problem 61 is right here. But I'm not gonna make you listen to the audio. Okay, this is a first. Okay. Maybe someday I'll be famous and you'll have to wait through some 30-second commercials to get to the audio, but thankfully you don't have to do that yet. Okay. So that's just basically refreshing our website in your mind. If it's not on our website, it doesn't exist. I gotta let someone in the room, excuse me. If it's not on our website, it doesn't exist. If you want it to exist, ask me and I'll put it on our website. But when you're asking questions about when's it due, what's due, when's it due, I'm gonna send you right back to the website. And if I have an error on it, then I have to eat that error. But that's what controls our class. Okay, now let's do some math. Unless, and if you want to ask any particular question about everything on the website or elsewise, you go right ahead. But now we're going to go back to work. Okay. Questions. Let me help you out there too, because I know you're focused on the XYZ homework, as you should be. But don't just shoot me questions from the screens there. I mean, I'm going to leave that totally up to you because it's your homework. But any problem you see in that XYZ homework that you're working on, there is a problem in the book, and several, in fact, that are like it. So if you're trying to puzzle out a particular kind of problem in your XYZ homework, find the problem in the book. And then ask that either here, email, elsewise. And that's how I want to organize the videos, the solutions that I post, the written solutions I post. I did not show you that. So here's an example of a written solution I posted to a problem. The start of what we're going to do today. So I want to keep those things organized by the problems in the book because each of you have different homework problems on your screens. The computer kind of changes that up. Okay, so answer any question you have, but not the questions from your homework. Find the problem in the book that matches your homework question. Very good. So now we're going to dive into sections 1.4 and 1.5 in this week, this one session that comprises our week. So I want to hit the highlights for you here, and then I'll illustrate each of these on our paper. The big important points are those three famous right triangles, and I'll redraw them for you in a second. The 15-75-90, the 30-60-90, and the 45-45-90. Those values are really, really valuable. You might ask, how do I deal with a 12-degree angle? Well, we'll get to that. But if you know the major ones, then you've got half the battle already settled. We, at the end of our last hour, talked about the definition of the 6 trigonometric functions for an angle and standard position, and we'll redo that now. And what I want to emphasize is that if you know a point on the terminal side of an angle, you can name all 6 trigonometric functions immediately. You might have to do a little calculation or arithmetic, but all you need is an angle and a point on the terminal side of that angle. Even from one trigonometric function, you can name all the other 6 if you know what quadrant your angle is in. That sounds kind of remarkable. First of all, like from one function, I can name all 6 of them. Then why do I need 6? Oh, that's a fair question. But it's not exactly just from one value. You have to know a value and the location of the angle, and we'll illustrate that. Since the plane, we've chopped up our plane into 4 quadrants. Make sure you pay attention to the signs, S-I-G-N-S, of the X or Y values, the signs plus or minus of the X or Y values. And that depends on the quadrants that the points are in. You also need to be prepared to work with these special angles that are not in any quadrant. Remember, the quadrants from the x-axis and the y-axis are labeled quadrant 1, counterclockwise from the upper right, quadrant 2, quadrant 3, and quadrant 4, the Roman numerals. So based on whether x or y is positive or negative, that's going to change the sign. But there are some angles that we say do not belong to quadrants. And that is the 90-degree angle, straight up, the 180-degree angle, flat, the 270-degree angle, 90 degrees short of a full circle, and the 360-degree angle. These angles that land on the axes, x or y axes, these are called the quadrantal angles. You don't have to remember a fancy name, but if you hear someone say quadrantal angle, then you know what they mean. That means they don't land in a quadrant. They're the borders of the quadrants. So you also need to be prepared to work with these. Wrapping up, and especially in your written homework, always want to be able to draw and label accurate diagrams of your angles and their reference points. And today I'll show you a quick way to organize that we're going to preview some things we're going to do next week. It's called the reference triangle. And then the content of 1.5, we're going to begin to explore the relationships between the 6 trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. These are the names of the 6 trigonometric functions. And those relationships between these functions, they have a special name. They're called identities. So that's what we're going to begin to work on in a small way in section 1.5. And when I say to remember all these things and identities and things like that, I want to point you back to one of our formula sheets. So different people do things differently in different classes, right? If we were in a face-to-face class, I would be having a formula sheet, and people would say, can I have formulas on the test? Can I make a formula card? And I don't have any problem with that, except, one person makes this formula card, the other person makes that formula card. Oh, his was better than mine. Well, that's your responsibility. No, I don't want to even have people start that argument. So if I was giving you a test in a traditional class, I would make a formula sheet and staple it to the test. Just say, everybody got the same formula sheet. And that is this fundamental trig identities page. So you can start with the fundamental trig identities. That tells you the basic identities. And if I could blow that up a little bit, it defines the 6 trigonometric functions that we did last time based on a point on the terminal side of an angle. So this is a picture that tells you what these 6 functions are. Someone else in the room here? No problem. So this picture says if you have an angle theta on the terminal side of point X and Y, that means, oh wow, that's a terrible drawing, isn't it? Look at that. I'm going to have to redo that right after class. I put Y on the X-axis and I put X on the Y-axis. My goodness. Nobody complained about it either. Okay, let's redo this later. X on the X-axis, Y on the Y-axis. If you have this point XY, this is how you define the trigonometric values. Oh, standard position is just the way you always roll. So if someone says, and that's a good example, so I'll write it on my paper in a second. Standard position just means you are comparing all the angles from the same starting point. Standard position is with the initial side on the x-axis. And you will remember, and I'll show this paper in a second. So let me pop back to there. This is the x-axis. If I say 30 degrees, I mean 30 degrees from the positive x-axis. And that's called a positive angle. When you go counterclockwise, it's called positive angle. But if I said negative 120 degrees, I would also say you start from the positive x-axis, you go clockwise this time, down 90 and 30 more. That angle would be negative 120 degrees. So when someone says standard position, they just mean they're always measuring from the same starting place. Now you want the word coterminal, no problem. This angle ends on this line, this ray, but I could have also landed on that place by going the other direction. I could have said, oh, let's go 240 degrees in the positive direction. So that's coterminal. 240 degrees is called coterminal with minus 120 because it landed on the same terminal side. Let's try it with 30 degrees. If I went once around and came back to 30, that would be 30 degrees, or 360 plus 30, that would be 390. These two angles, they are different angles, but they landed at the same terminal side. So they're called coterminal. Okay, good. Worth practicing again. I want to go back to that formula sheet though. So on a test in traditional class, you'd have this stapled to your test, and we have more formulas to go. These are just the beginning ones. Notice the sine and cosecant are related. Sine is y over r, cosecant is r over y. So what is cosecant? Cosecant is the reciprocal of sine. So that's why cosecant theta equals 1 over sine theta is called an identity, a relationship between cosecant and sine. That's called a reciprocal identity. And there are 6 reciprocal identities. Secant is the reciprocal of cosine. So you write secant is 1 over cosine. But you could also write cosine is 1 over secant. So we're going to go through reciprocal identities. Later, I'll tell you what the co-function identities are. Not today, but someone else in the room. We've talked about the Pythagorean identities, just the cosine squared plus sine squared equals 1. We can mention these other 2 later. The quotient identities. Do you see that sine is y over r and cosine is x over r? So if you take y over r divided by x over r, you get y over x. So there's a quotient. The book calls it the ratio identity. Sine theta divided by cosine theta is tan theta. All these relationships between the 6 functions, all these identities, they're what allow you to name all 6 functions just from very little information. On my introduction, I said, let's beware of the signs. I can't believe I put y on the x-axis and x on the y-axis. That's ridiculous. But you have to pay attention to the signs of x and y. So here's a little kind of colorful chart to tell you about sine and cosecant. If sine is negative, cosecant is negative because they're reciprocals. Cosine and secant, tangent, cotangent. Notice in the first quadrant, all 6 of them are positive because x and y are positive in the first quadrant. R, radius or distance, is always positive. But in the second quadrant, sine and cosecant are still positive. That's that red mark. So between 0 and 180, sine and cosecant are positive. On the other hand, between minus 90 and 90, I could call this 270 angle minus 90 also. Between minus 90 and 90, cosine and secant are positive because they depend on the x. And in these two quadrants, x is positive. Tangent and cotangent are kind of goofy. If x and y are both positive, then tangent is positive. So is cotangent. If x and y are both negative, tangent is positive because the negative sign will be canceled out, and so is cotangent. So I don't know if the color or even this pattern helps you remember things, but just be aware of the signs. Okay, we're going to give you other identities later, but these I called the fundamental identities, the most basic ones. We have not talked about the word radians yet, and we have not physically talked about cofunctions or cofunction identities yet. So they're coming. Hang on to those. Okay, now let's go back to our list of things to do. So I want to remind you of the three famous triangles. And we just reminded you of the definition of 6 trig functions. And then we're going to give you a demonstration. So remember these 3 famous triangles. I'll draw them here for you on the paper. A right triangle with the 2 legs having the same length. And if you make the legs have the length 1 and 1, and the hypotenuse has the length square root of 2. This is the 45, 45, 90 triangle. You'll see why I want you to remember that ratio shortly. Let's draw a 30-degree angle. Now, sometimes that bugs people like, that 30-degree angle doesn't look very good. I can't draw a 30-degree angle. I'll give you a tip. Do you see that for the 45, 45, 90, I made these 2 legs equal? They were both 4 boxes. I could have made them both 3 boxes. You know, your choice. But if you want to draw an angle that's very nearly 30, 60, 90, do this. Do 4 boxes by 7 boxes. I'm assuming you have a piece of graph paper here. You could have gone 4 inches by 7 inches if you had a ruler. Okay, this I just drew 7 boxes wide, 4 boxes tall. Connect with a line. Now be very careful. Don't go to someone and tell them this is 30, 60, 90 exactly. But this is darn near 30 degrees. Close enough for a drawing. If you want to be really, really picky, if you draw it 4 by 7, it's about 1/4 of a degree off. It's 29 3/4 degrees, kind of. But I want you to remember this ratio. 1 for the short leg, twice as long for the hypotenuse, √3 for the long leg. That tells you how to navigate back and forth between the sides. This is the 30, 60, 90 triangle. Lastly, the 15, 75, 90 triangle. And you say, I could draw 45 degrees. I'm not so good at 30 degrees, but thank you. Oh, notice that that also tells you how to draw a 60-degree angle if you wanted to stand it up. But you say, how do I draw a 15-degree angle? I'll try to cut this in half. Here's another tip. If you want a 15, 75, 90 triangle, then draw a triangle that is 15 boxes. I don't think I'm going to get 15 boxes here. Let's try it right here. 5, 10, 15. Did I do 15 boxes there? 5, 10, 15. And 4 units tall. And if you do that and connect this line right here, you get a 15, 75, 90 triangle. Now again, it is not perfectly exact, but this is accurate, even more accurate than the one above. This is accurate to 7/100ths of a degree. So it's just a good rough drawing. And here, remember the side links I want you to remember are 4 √6 plus √2 for the long side, √6 minus √2. I made that too tight for the short side. Keep these triangles in mind. Let me show you how to use them. So, first example. What if I asked you for the sine of 135 degrees? First step is to visualize where 135 degrees is. And you can say, with just a rough drawing, 135 degrees. I know this is 90. I know this is 180. 45 more will get me to 135. And 45 degrees is a 45, 45, 90 triangle. So this angle is 135 degrees. What's the sine of 135 degrees? Well, just think about a point on this triangle, point on this angle. And X and Y have got the same size here. Like this is like -3 and +3. That's one point. How about -1 and +1? That's another point. Now from that, can you name how far this is from the origin to that point 3 minus 3? Well, yes, you can, because you've got the famous 45, 45, 90 triangle. If this is 3 and this is 3, size-wise, what's the hypotenuse? 3 √2. That's all you have to do is multiply by √2 leg. If this is 1 and this is 1, it's not that important to draw this to scale, but I'll try. Then this is 1 times the square root of 2. So now you know that X, Y, and R are given. The R is √2 if the X and Y are -1 and 1. Or if the X and Y are -3 and 3. Notice that the X has to be negative because I'm going in the negative direction. This R would be 3 √2. Either way, the sine of 135 degrees, which is Y over R, either 1 over √2 or 3 over 3 √2 is the same number. And that is the magic of a similar triangle. So now I know the sine of 135, but actually I know the cosine, the secant, the tangent. I know all of them. I know all of them because after I say X, Y, and R, I can fill in all 6. In the next example, let me fill in all 6. But this is the game they're trying to make solid in your mind in sections 1, 3, and 1, 4. Let's try it a different way. Let's say I give you a point like 4 and -6. And I say that's on the terminal side of an angle theta. Sorry, paper was too high. And ask you to find all 6 trigonometric function values. In a second, I will illustrate again why we use this fancy word trigonometric. But first step is just draw the angle. And when you say 4 and minus 6, you got to say, where am I? I'm in the positive x side and negative y side. And you don't have to count 4 and 6 boxes wise, but if you have room, it doesn't hurt. Let's go 4 boxes over, 6 boxes down, 2, 4, 6. I'm right here. You can label these sides 2 and 4, minus 2, minus 4, minus 6, and then draw an angle that goes through that point. Now, is that angle a famous angle? I don't think so, because it's not, these are not a famous ratio. It doesn't match my 30, 60, 90, 45, 45, 90, 15, 75, 90. You know what? I don't know what this angle is. Or do I want to say the angle like this? I could say the angle either negative something or positive something, but I don't need to name the angle. I think this is like, to me, if I was guessing, I would say probably like negative 55 degrees. Maybe it looks like negative 60 to you. But I don't need to name the angle because I have the x and y. And from the x and y, I can find the r. Remember? R squared equals x squared plus y squared. So I just insert 4 squared plus minus 6 squared. Give me 16 plus 36, which gives me 52. You should simplify that as far as you can. There's any perfect squares inside 52, 4 times 13. So I'm writing down every single step here, but this radius is 2 root 13. You could ask a calculator what 2 root 13 is if you wanted to know. And so we will, but be careful. Don't use an abbreviation or an approximation unless someone tells you to. But I'm just curious what 2 times the square root of 13 is about. Got to be between 7 and 8. I'm thinking square root sign, got it, 13, go. 7.2, roughly. I do not want you to approximate. I want the exact values if they say exact values. And I know that there's some issue in the homework system, whether it uses exact values or not. We'll deal with that. But always give the exact values if you can. And here I can. I know the exact value of R. And now I'll start rattling off the sine theta. Y over R. Negative 6 over 2 root 13. Now that is the ratio, but that is not the answer. You're always required to simplify when you can. So 6 divided by 2 is 3 divided by 1. This is negative 3 over root 13. That's got a radical in the denominator. For a moment, let's just leave it there. Pretend nobody cared about that. Cosine theta. You have x over r, 4 over 2 root 13. Again, you simplify if you can. 4 divided by 2 is 2 divided by 1. Tangent of theta is just y over x. Minus 6 over 4, simplified minus 3 over 2. And then the other ones, you can just run as the reciprocals of these. For example, once you've found out what tangent is, then cotangent is just the reciprocal of that. You don't have to do extra work. You just say minus 2 over 3. Once you figure out what cosine is, if you remember who its partner is, its reciprocal partner is secant. So instead of 2 over root 13, it's root 13 over 2. Now here the sine The reciprocal partner of sine is cosecant. And that is minus root 13 over 3. Minus sign I either keep in front or on the top number. These are the 6 trigonometric values. I did not rationalize denominators. Maybe we'll do that in the next example. But I want to emphasize this. Just from a point, that tells me what quadrant I'm in. That tells me whether my x's and y's are positive or negative. I have to make this match the reality of the picture. It tells me what the r is. And then it tells me the 6 functions, because I remember sine is y over r, cosine x over r, tangent y over x. The author is very blunt about this. He just says memorize them. And that's what you have to do. But I can give you some tips for memorizing them. And that is, you notice how they come in pairs. Memorize them in pairs. If you know tangent is y over x, then you know its reciprocal cotangent is x over y. If you know that cosine is x over r, then you know its reciprocal secant is r over x. If you know that the sine is y over r, you know its reciprocal cosecant is r over y. Now be careful about the word reciprocal. Some people think because cotangent and tangent are reciprocal, that co means reciprocal, and it does not. Cosine does not go with cosecant. So you have to remember who the partners are. That's one of your tasks. But that means if you remember 3 of them, the other 3 come for free, always. Or if you knew one of these, you could find the other one back here. Okay? So when I say reciprocal function, I mean 1 over cotangent is tangent and 1 over tangent theta is cotangent theta. These are the reciprocal identities, and they are listed on your formula sheet. Later, I will explain what the word co means, and we'll talk about the co-functions, sine, cosine, tangent, cotangent, secant, cosecant. And I'll tell you about the co-function identities. But right now, we're just talking about the basic reciprocal identities. Okay, good. Next question. Let's say I give you an angle. I'm just running through some examples of how people can ask you for the angles. Let's say I give you an example where I want you to find, all 6 trigonometric function values of the angle theta is, let's get busy. Let's get kind of a nasty one. How about negative 165 degrees? So I'm going to make it negative. I'm going to make it a strange number, maybe. And now we're going to find all 6 trig values. Okay. Pick up a different color here for variety. First job is, where the heck is that angle? So I had to think about negative 165. This is 0 degrees. This is 180 degrees. If I go counterclockwise direction, it's also minus 180 if I go the clockwise direction. So you can also say to yourself, oh, that's also minus 180 degrees. And then minus 165 looks accessible. You say, okay, it's minus direction. It's nearly 180. How far short is it? Oh my gosh, it's 15 degrees short. So I'm going to draw my best I can, a 15-degree angle here. Doesn't have to be perfect. It's 4 to 15, right? How about 2 to 7.5? 1, 2, 3, 4. You know, I don't even have to make that perfect. I'm just going to draw something that's decent. This looks like it could be 15 degrees shy of 180, doesn't it? Just make it fair, not at 45-degree line. So here's the angle. Theta equals minus 165. Now let's do all 6 trig functions. And you say, I can't do that. You didn't tell me what the x and y are. You didn't tell me what the x, y are and r are. Oh, but we do. We know the ratio of this famous triangle. That if I lay down a 45, 45, 90, I know that ratio, but this is a 15, 75, 90. And I'm allowed to lay down any ratio I please that's true. Back to this paper. See, when I said minus 3, 3, the triangle I created had the same ratio as minus 1, 1. Notice I labeled the sides here only with positive numbers because I was talking about their length, but the minus 3, 3 is the name of a point that went backwards 3 and up 3. The minus 1, 1 is a point that went backwards 1, up 1. So I can use the famous ratio of 4 root 6 plus root 2 for the long side. Plus will give me the long side. Minus will give me the short side. And now that I know the x, y, and r, I can find the what? 6 trig functions. Now I got to do one thing though. Remember, this x is in the negative direction, so I have to technically slip a minus sign in front of that. I'm going backwards. I have to slip a minus sign in front of this. I'm going down. So the name of this point right here, x comma y, legally is minus 6 plus root 2 quantity minus root 6 minus root 2 quantity. If you want to distribute the signs, I call it minus root 6 minus root 2 minus root 6 plus root 2, as long as you distribute them honestly, then you're okay. Do I have to use the Pythagorean theorem to find r? No, I already know r because I know that famous triangle. Okay, now we just rattle them off. Sine theta. Theta is 165. I could write, since I said theta was minus 165, I'll just write theta. Y over r minus root 6 plus root 2 over 4. Cosine theta, x over r minus root 6 minus root 2 over 4. Tangent of theta, y over x, make sure you get in the right order, minus root 6 plus root 2 over negative root 6, negative root 2. Now these are crazy numbers to be sure, and if I wanted to approximate them, I could with a calculator. But first, let's just practice writing down the exact ratios. But just to give you a demonstration, what's minus root 6, what's the sine theta? So I use parentheses, minus square root of 6 plus square root of 2. And every calculator is kind of a different way to operate the roots and stuff, so I'm being very careful with my parentheses. Divided by 4. Just let me check something there. Got it. Okay. And as a number, that is minus 0.2588. I'll take 4 digits there. The nearest 4 digits, 0.2588. Now, if I showed you this trick, if someone showed you this trick, you don't want to retype that, right? Just hit second function entry on your calculator, and it'll give you the last thing you typed. So that'll let me go change that minus plus sign to a minus sign. Also, pay attention to that. This is the opposite of root 6. This is a minus root 2. The opposite key is down here if you have to create a negative number. Subtraction key is over here if you have to subtract. What's that value? Minus 0.9659. And now, if I wanted to take the last two numbers and divide them, I could just go over there, delete that, and type y over x. This is the y over r. This is the, oh, I got to keep straight. I want the plus sign on top, right? So I'll do that in a second. Minus square root of 6 minus square root of 2. Get a parentheses in there. But go back and make this numerator part positive. Okay, it'll show me what I wrote. Plus sign on top, minus sign there. And it says 0.2679. So you can enter these numbers and approximate them on your calculator too. By the way, I could also ask the calculator what the sine of minus 135 degrees is. Now, I got to be careful. That is not minus 135, minus 165, excuse me. Sine of minus 165 degrees. Notice it gives me that 2588 right there. So you could practice all of these. If you do that, make sure when you enter degrees that your calculator is in degree mode. So under the mode button, make sure you're using degree mode. We will talk about radian mode later, not in this sections. Okay, find all 6 trig values. I have sine, cosine, tangent. Maybe just for the sake of time, I'll let you finish their partners, cosecant, secant, and cotangent. But remember, all I have to do is flip these over. So cosecant is the reciprocal of sine. So I just write 4 over minus root 6 plus root 2. Approximate it if someone asks you, but don't approximate it unless they're asking you to. Also, if you're approximating something, put a little wiggle on the top just to tell people that you know it's not exactly that you know that there are more digits, but those are the first few digits. We will talk about rounding later, and we will talk about something later like how many digits should I use? And maybe mess around in other classes, science, chemistry, something like that. When someone says, how many digits should I use? They're talking about significant figures. Sometimes some people say sig figs for short. Sometimes significant figures or sig figs get like a dirty name, like, oh no, that's impossible to work out. No, I can explain to you how to use significant figures properly. The idea is when you round off, you don't want to give someone too few numbers. You don't want to give someone too many. So what is the appropriate number of decimals to use? We'll talk about that later. How about this example right here? Because we've already talked about paying attention to the signs. Maybe I'll do a quadrantal angle. But what if I gave you one trig function value and the quadrant of theta? Let's do that as an example. So what if I told you, let's get non-trivial here. Let's say the cosecant is theta. The cosecant of theta is minus 7 over 4. I'll just make up some numbers. And I'll tell you that theta is in quadrant 4. Can you draw this theta? And can you find the other trigonometric function values? I did not tell you what theta was. I just told you where it was, and I gave you one of the 6 values. So I'm going to emphasize trigonometric here again. Why do we use that word? First, let's just draw a credible picture. Now, I have to remember what cosecant is. And in fact, since I know cosecant is the partner of sine, remember, I already know 2 of the 6. This is minus 7 over 4. That makes this minus 4 over 7. Because secant is reciprocal with cosine, and cosecant is reciprocal with sine. But now I have to think about this. Remember, sine is what? Y over r. So I can use the 4 and the 7 as the y and the r. I can use any ratio I please. I got to be careful with a minus sign, though, because never, ever call r negative. So don't say, that even though cosecant is r over y, and you said minus 7 over 4, that's the way you spoke it. Don't call r minus 7. What we have here is x and y and r, and I know I could use 7 for r. Don't use a minus 7. But if I use a 7 for r, that means the y has to be the minus 4. Now I need to find out what x is. And how am I going to do that? Pythagorean theorem. If I take 7 and square it, that'll give me x squared plus minus 4 squared. 49 is x squared plus 16. That means x squared is 49 minus 16, 33. That means x is plus or minus the square root of 33. And there's no perfect squares inside 33, so I'm just going to have to eat it. Square root of 36 is 6. I know this number is close to 6, but I'm not worried about approximating right now. Which one should I choose, plus or minus? Well, that's back to the quadrant. If I'm in quadrant 4, is x positive or negative? Well, this is quadrant 4 over here in the lower right corner. So that means next to the x-axis, this x is positive number. So I cannot choose both of them. I have to choose one of them correctly. I will choose root 33 positive. You heard me say that this was kind of about 6. So you could ask your calculator 5.8 or something. I just want to draw a credible picture, right? So I won't put this on the screen, but I'll just ask my calculator what the square root of 33 is. 5.7. 5.74 approximately. So let me draw something that's about 5.7 and 4 in proportion. That means just a little bit longer than it is tall. So here's the angle theta. I don't know how many degrees that is, but it's over here in quadrant 4. Let me introduce this word to you, reference triangle. This triangle I'm drawing is called the reference triangle Because if I put the 7 here, and I put a -4 here, now that doesn't mean this side is -4 units long. It means I'm going down 4. So think about it that way. The length of that triangle side is 4. The length of the hypotenuse is 7. But I'm going in the negative y direction, so I could write -4 there. And what did I just discover here? This side has to be 33, or about 5.7, 33 root. But now that I know that point, right root 33 down -4. Now I can know all 6 values. What's the cosine of theta? X over r, root 33 over 7. What's the tangent of theta? Y over x, -4 over root 33. I'm not doing the rationalized denominator yet. What's the secant of theta? Who is the secant partner with? Cosine. So that will be 7 over root 33. Notice I did not say secant. Is that r over x or r over y? No, I just said secant is the reciprocal of cosine. So I just flipped over cosine. Cotangent is the reciprocal of tangent. So this is minus root 33 over 4. So I just want you to be excellent at playing this game of drawing an angle. Drawing, this is called the reference triangle. It's the right angle that you build on the x-axis. When you draw the reference triangle, you always draw it standing or hanging, either way you want to say it, from the x-axis. And you label the sides according to the information you're given. Although it might look funny to call that side -4, it means I was going down 4. If you want to draw it as a positive number, go ahead. But remember that y is negative in this quadrant. Okay, good. Now I'm going to switch gears a little bit. So let's go back to our plan for today. Notice you should always be prepared to do, excuse me, the quadrantal angles. I'll do a quadrantal angle for you next. Drawing and labeling diagrams and their reference points and their reference triangle. We've illustrated that. And then we'll start looking at these relationships. Let me draw one more example of quadrantal angle. What if someone said, give me the sine, cosine, tangent. Sorry, I'm not writing very clearly. Cosecant, secant, and cotangent. I haven't filled in the angle yet. You have to fill in the angle. But notice how when I write 1, I always write all 6. And notice how I always put the reciprocals side by side. Handy to remember. But let's say sine of minus 90 degrees. Cosine of minus 90 degrees. Tangent of minus 90 degrees. Cosecant of minus 90 degrees. There's something you have to be careful when you have an angle on the axes, right? Let's draw it. X-axis. You can always label these x-axis, y-axis. If you like, it's kind of handy to say x-axis, y-axis instead of just x and y, because we're frequently using x and y. Minus 90 is going down here. You could have also said 270 degrees, but the question said minus 90. Now pick a point on this terminal side. And then you kind of have a problem because one of the points has got to be 0. You could say x and y is left and right 0, down negative sign, down 1, or down 3 or down 5. You could pick any ratio you want, but where am I going to get in trouble? What's x over r? What's y over r? What's y over x? See, if x is 0, it's going to screw up one of these fractions, right? First of all, let's just do the sine. y over r. How far is this point away from the origin? Even that you have to think about, because you don't have a triangle here. But you could say this is exactly one step, positive number, away from the origin if you went down one step. So y over r in this case is -1 over 1. But just simplify it, call it -1. What's x over r? 0 over 1. But you must simplify it and call it 0. Don't give an answer of 0 over 1. Simplify always. Here's a pain comment. What's y over x? -1 over 0. And you're not even allowed to say that, because there's no such thing as divide by 0. In that case, you have to say undefined. Undefined means that's not a number. R over y? Well, what's the reciprocal of -1? It's also -1. What about r over x? Oh my gosh, I'm screwed up again. X is 0. I can't do that. Don't write 1 over 0. That's not the answer. The answer is undefined. And what about x over y? Cotangent? Well, the reciprocal of undefined would be 0 over -1. That is legitimate. When you take 0 divided by a number, you always get 0. But when you take a number divided by 0, you get nothing. Okay, so quadrantal angles, you got to be prepared to say undefined at the right place. Question from Austin. How do I know when I have to rationalize denominators? And I'll make this our standing rule. If we want you to rationalize the denominator, we must explicitly ask you. So for example, in the written homework, I said, and rationalize the denominator if necessary. Many times people do not mind. Many times, though, it's helpful. So let's make this our standing order. If it says rationalize the denominator, you must do it. If they don't mention it, then you don't have to do it. That'll be our standing rule. And he follows a similar rule in the book. Okay, good. Now I just want to say one more thing today, and you can turn loose on some of the homeworks. Now, everything we've just done today would be enough to help you do that written homework. So you can start to look at that, talk about it, find similar problems in the book if you want to ask a question. But I want to begin to explore the relationships between sine, cosine, tangent, secant, cosecant, cotangent, and not just the reciprocal relationships. So for example, sine of theta is the reciprocal of cosecant of theta. Or if you want to say it the other way, cosecant of theta is 1 over sine theta. What does that mean if I told you to multiply sine theta and cosecant theta? What happens if you multiply 7 times 1/7? Well, you get 1. And here, sine theta times cosecant theta, it looks fancy, but realize it's just 1. Because cosecant theta can be replaced with 1 over sine theta. 1 over sine theta times sine theta is 1. This is an example of what people call a trigonometric identity. This looks like some fancy equation, but a trigonometric identity means these two things are the same. Can you show me that they're the same? You show me that they're the same by telling me that you know what cosecant is. Cosecant is 1 over sine. So sine times 1 over sine is 1. That, in the math language, that's called proving a trigonometric identity. Let me give you a very other basic one. What if I said cosine of theta times tangent of theta equals 1? Can you prove this? Can you show me that this is always true? Well, let me change that. Not 1. Let's make it, 1 was the last problem. Let's make it sine theta. Maybe it's not always true. But if you remember the ratio identity, the tan theta is sine theta over cosine theta. Then you realize when you multiply by cosine theta, sine theta is all you have left. You say, I proved it. I showed you that they were the same by simplifying that side until it matched. That's called proving a trigonometric identity. So sometimes you get, let me pick one out of the book here. I'm in section 1.5 right now. He's got a whole list of things you can prove. And here in section 1.5, he starts out with some kind of mellow ones. He says, this is problem number 51 in section 1.5. Show that this statement, this equation, is an identity. Now I have a video demonstrating one like this too. So you make sure and check that out if you want to see even more explanation after today. We're actually going to be working on trig identities often, but in the section 1.5, he just wants to introduce you to some mellow ones first. Sometimes they can be pretty complicated. Look at this equation. They don't look the same at all. And the only thing I have going for me is someone told me that they are the same. So then I'm going to investigate, say, okay, someone said these are the same. That means I should be able to simplify this until I get this secant theta. This is from the book section 1.5, number 51. So after, if someone tells you that they can be simplified, that they are the same, then it becomes a game. How do I turn this into that? Now there are some rules to this game. And that is, you generally take one side and turn it into the other. You do not work on both sides at the same time. And you generally take the more complicated side and try to turn it into the simpler side. But you can still use your rationality, right? What is secant? Whose partner is it? It's 1 over cosine. So if I could make this into 1 over cosine, I'm done. I did it. Say, this isn't 1 over cosine. Where are you going to get 1 over cosine? Well, let's just be patient. Let's try to simplify this. I could start by saying, I know tangent is sine over cosine. Maybe that will help me. And your first reaction is, no, that didn't help. That made it worse looking. But sometimes this is a good tip. If you write things in terms of just basic sines and cosines, it might help you find your answer. This does not look promising yet. This is sine theta times sine theta. It's written sine squared theta. But I will say this for myself. I now have a cosine theta in the denominator, almost, not nearly like this, but on the way. What if I had to add these two people? The next thing I would say is, oh, what if I use common denominators? If I multiply the top and bottom by cosine theta, I could write cosine theta as cosine squared theta over cosine theta. Well, now I have a common denominator of cosine theta, so at least I have a denominator called cosine theta. But if I put those two together, I get so much more. This is why you have to know your fundamental identities by heart. Sine squared plus cosine squared, sine squared theta plus cosine squared theta is always equal to 1. So anytime you see sine squared plus cosine squared, just one of these and one of these, squared, squared, same angle, you can immediately replace it by 1. Now, sorry, I'm shaking my camera. That assumes you memorized this Pythagorean identity, right? So you have to know the identities on this sheet. Every time you see sine squared plus cosine squared, you say 1. In fact, every time you see 1 plus tangent squared theta, you could say secant squared theta. And likewise here, I'll show you the other two later. But look at what we've done. One step at a time, we took this side, just did ordinary legal things. And now I've arrived at 1 over cosine. And then I say to myself, oh my gosh, that was secant. That is what I want. So I've just made the two sides match. I've proved to you one step at a time that these were the same. And they didn't look the same at the beginning. This is called proving a trigonometric identity. Oh, I want to pay attention to what you wrote in the chat. That's a good comment. Sometimes if you want to say undefined, like 7 over 0 is undefined. Sometimes in math, people also abbreviate that as does not exist. Thank you for pointing that out. And in the homework tips on the website, they tell you how to enter numbers. They tell you if you want to say undefined or does not exist, you just enter DNE like that. I'm not always cool on abbreviations because abbreviations sometimes confuse people, but DNE, does not exist, is a kind of a standard abbreviation of math. If I was writing it in English, I would prefer to write the word undefined. But if they want the answer entered in that system, does not exist, when you say something divided by 0, then you have to follow their instructions. Okay, thank you for pointing that out. Okay, but here what we did is called proving the trig identity. And so in section 1.5, he just gives you a pile of these puzzles. Think of them as little puzzles. They can get worse and then get easier, and we'll see some worse ones. But first, he just has you warm up very nicely on some medium ones. Okay, what do we got to get to today? And so this is kind of the whole list that I wanted to do. We will talk about identities a lot more, but I just want you to begin to explore these relationships in 1.5. And that means, I don't know, if memorize is a dirty word to you, but the author says, you're just going to have to step up and memorize these relationships until you know them like the back of your hand. I will show you ways to make them easier to remember. Like, you don't always have to remember 6. You usually have to just remember 3. Sometimes you just need to remember 2. They always come in partners. They always come in pairs or triples. Pythagorean identities. If you remember 1, you can remember the other 2 automatically. So it's not as imposing as it looks, but you do need to know these basic relationships. I cannot believe I wrote Y and X here like this. I mean, I've had this sheet passing out to students for a couple of years. I bet what happens is someone brings it up and then I just cross it out and write X and Y. And then I never remember to change my sheet. This afternoon, I'll change this sheet. Okay. Dig into these sections. You can send me a question if you want to see a video or a solution. You are working on the XYZ homework and you're working on your first homework problem. Remember that both of those are due next Tuesday. The goal is when you come back to session on Monday, if you have a question you need to wrap these up, then that's where you're going to have to ask it. Or apart from individually too, but you have an opportunity to ask in class about either of these assignments before you hand them in. Next time, I'll also talk about how to turn an image into a PDF if you just want to make that easy to trade with people. One more thing before I say goodbye is that I only issued you invitations to class sessions for the first 2 weeks just to make sure I had everything working. Sometime later this week, I will issue you calendar invitations to all the rest of our Monday, Wednesday meetings. And remember, we lose a Wednesday at Thanksgiving. But I'll issue the calendar invitations for all the rest of our meetings. And then if you like to use a calendar, then that link is in your calendar. Okay. You guys relax and you have a good afternoon. It's not bad to go outside, just a little bit cool, put on a sweater. And we'll check in with you later. Thank you.